Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 29, rates and orders of reactions, part 2, zero-order reactions. Today's objectives are to learn how to recognize zero-order processes and use best fit equations from concentration time plots to determine drug initial concentrations, rate constants, half-lives, and drug concentrations at specified time intervals. We are also going to spend a little bit of time to discuss the physical significance of a zero-order rate constant. So this is very important. I also would like to remind you that the only way to accurately determine the order of a reaction is to actually carry out experimental measurements of the concentration change of the reactant with time at variables concentrations of reactants. Determining the order of a reaction from balanced chemical equations is only a crude approximation. Lastly, I would like to remind you that in lesson 27, we have discussed in great detail logarithmic and exponential equations. And if we are to carry out pharmacokinetic calculations accurately, we need to make sure that you are able to perform logarithmic and exponential transformations. So I would encourage you to study lesson 28 and of course lesson 27, okay? Now, as the name implies, the rate of change of a substance in zero-order reactions can be written as dc dt is equal to k times c to the 0. Now, I remind you that the rate law is written as dc dt is equal to k times the reactant concentration to the order of a reaction. Since the order of a reaction is 0, I have c to the 0, which is 1, and therefore dc dt for a zero-order process is equal to the rate constant. So this is very important. In zero-order reactions, the rate of change of a reactant, or a drug in this case, since we study drugs, is independent of the reactant or drug concentration. That's very important. So regardless of the concentration of the drug, the rate of change or the rate of the reaction is always constant and is equal to k. Now, if the rate of change of the drug with time increases, then I have plus k. If the concentration of the drug with time decreases, then I have a minus k or a negative k, okay? Now, when do we have zero-order process? Now, in our body, we rarely have zero-order process, but in certain cases, especially when the pathways are saturated, we may experience zero-order processes. Now, for an increasing rate, for example, that could be, let's say, drug absorption. So when the concentration of the drug in the GI is high enough to saturate the pathway of absorption, then the rate of absorption in the blood, and therefore we have increasing concentration in the blood, is constant and is equal to k, okay? Now here, this process will refer to elimination of metabolism, for example. So metabolism here, just one example. And it could be observed when the drug concentration is high enough to saturate all enzymes. Then the metabolism of a drug is constant, independent of the drug concentration, okay? So all of these are written in these 3 paragraphs for you to read. Now let us now take a look at figure 12.1. So obviously here we have the rate law, dc dt is equal to k, and we have plus or minus sign here, right? Now here, dc dt is my y-axis, and c is plotted as a function of concentration. And what you see here is that regardless of the drug concentration, the rate of change of the drug with respect to time, or the rate of reaction, is constant and is equal to -3. So therefore here I have an elimination process or a decaying process. So here I definitely have a negative value. So what is the value and units of k? So dc dt is equal to -3, and therefore k must be equal to 3. So we always report k's as absolute values. So again, I repeat, dc dt is equal to -3, and therefore k is equal to 3. The units of k, since this is plotted as a function of concentration, I will be having concentration over time as units of K. So it could be, for example, milligrams per liter over hour, okay? Now, of course, from this differential rate law, I would like to be able to calculate or determine drug concentrations per unit time. So for that, we need the integrated form of these equations. And here we have the integrated form of this equation, of the differential form, right? So if it is an elimination process, the equation is C equals to C0 minus KT. If it is an increasing process, C equals to C0 plus KT. Now, for the purposes of our lecture here in this chapter, we're only going to be dealing with elimination processes. But now we need to explain the symbols too. So this C here is the concentration remaining. So drug concentration remaining, okay? Not concentration eliminated. C0 is the initial drug concentration, here we are. K is of course the zero order rate constant, and T is the time, whatever units you have. Okay, so notice that this equation is linear, right? And if I plot C versus time, the slope is going to be K. Here we have. So the slope is going to be the rate constant. And the y-intercept is going to be the initial concentration in the blood or body, which is very, very important for us. Okay, so here we are. In this case, though, I didn't plot concentrations, I plotted drug amounts. So here is the mass of a drug in the body or in the blood, and this is the time in hours. So my equation here would be A equals to A0 minus, because it's decreasing, right, KT. So I plotted A versus time. K is going to be my slope. Here is the best fit equation, and you can see that the slope is -3. So notice, slope is equal to -K, which is equal to -3. Units is milligrams per hour. I'm very clear here. It's very important for you to be able to follow the mathematics here. Don't do any arbitrary actions here. Don't remove signs, okay? Just follow the equations. So since the slope is equal to -K, which is equal to -3, K is equal to 3 milligrams per hour, okay? A0 is my y-intercept. And you can see from the best fit equation that the y-intercept is 100. Graphically, it's clear here, okay? It's always a good idea to get the best fit equation instead of trying to eyeball it on the graph. In this case, it's easy, but in other cases, it could not be that easy. So this is why it's very important for us to use slopes and intercepts, because they can give us the rate constant and the initial drug concentration or drug amount in the body. So let us now discuss the half-lives. So half-life is defined as the time at which the drug concentration reaches 1/2 of its initial concentration. That is, when C is equal to C0. So if this is an elimination process, as I mentioned here, I'm just going to use my equation here, 12.3, okay, and substitute C equal to C0 when T is equal to T-half. So here C becomes C0 over 2 is equal to C0 minus K T-half. Cutting out the algebra, getting this guy there, right, or the other way around, I get C0 over 2 is equal to K T-half, and then T-half, my half-life, is equal to C0 over 2K. So this equation here, equation 2.4, allows you to calculate the time at which the drug concentration is going to be reduced to half. So the initial concentration is going to be reduced to half. Okay? For the zero order processes, the half-life is not very useful because the equation here is linear and you could actually determine it from a line, but still it's a valuable equation. Now here we have one example, 12.3, which we could actually apply what we have learned. So here in this plot we have the concentration of the drug in the blood of a patient determined at variable time intervals. So you drew blood after several minutes, right? Determine the order of the kinetic process, and we can say that since this is a line, since the graph C plotted against time is a line, this must be a zero order process, because the equation is C is equal to C0 minus KT. This is a line. The initial drug concentration, that should be there. So the initial drug concentration has to be 200. So C0 is equal to 200 milligrams per liter. The rate constant of the process is the slope. So remember, slope is equal to negative K, and that is the rate constant of the drug. Okay? And the half-life, so now we have the equation for the half-life, that should be C0 over 2K. Since you know C0, 200, and you know K from the slope, and we know how to determine slope, right? That should be C2 minus C1 over T2 minus T1. And we could do it here, we can eyeball it perhaps, any 2 points would do, but choose wisely the points. I would choose at time 0, because I know that is 200 definitely, and maybe I can choose one that is closer to the y-axis, so I would choose this one here. So this time is 1 minute, and that's maybe 195, right? So that should be, I'm just going to write it here because there is no space. So that would be 195 minus 200, and that's 1 minus 0. So the slope is minus 5, and therefore K is equal to 5. Okay? The unit is going to be milligrams per liter per hour. So I'm just going to write it here. K is equal to 5 milligrams per liter, because that's what I have, concentration, per minute. Sorry, I said per hour before. Correct it, per minute, okay? Okay, so now that I have K, I can determine the T half. I have an equation, right? So T half is equal to C0 over 2K, which is equal to 200 milligrams per liter over 2 times 5 milligrams per liter per minute. Okay, so this is milligrams per liter per minute. So that's 20 over 10, and therefore the T half is equal to 20 minutes. Okay? Liters and liters cancel out, milligrams and milligrams cancel out. So this is it. So here is our solution. 0 order, 200 milligrams per liter, and K is 5 milligrams per liter. Obviously, you understand that since all of this is determined graphically, it could be just an approximation, but it's a close one. It's a good one. And of course, the T half using our equation is 20 minutes. Okay? Now let us now proceed to the interpretation of the K, of the zero order rate constant. So here, as we discussed before, that's the initial concentration, and of course that is the concentration remaining, and therefore actually this is, since this is subtracted out of the initial concentration, this product must be having units of concentrations, and it must be the drug concentration eliminated. Okay, so I don't need to know how much was the initial concentration or the concentration remaining. If I have the K and the time, I can determine directly the drug concentration eliminated, which is very, very important. Okay, so for example, what does it mean when the zero order rate constant is 0.1 milligrams per liter per minute? It means that 0.1 milligrams per liter of drug is eliminated every minute. Okay? Okay, simple as that. Finally, let us solve a problem which requires the use of our equation. So here I have a control release dosage form, maybe a tablet or a capsule, and we have the amount there, so that should be the A0. Releases the encapsulated drug in the GI with a rate constant of 8.33 milligrams per hour. So I know that this is the zero order rate constant. Okay. How long will it take to release 80% of the drug? Okay. So basically, release 80% of the drug, basically that's 0.8. Okay. And 0.8 of 250, that should be 200 milligrams. So I need my product K times T to be equal to 200 milligrams. Let us take a look here so I don't have to write in a crowded slide here. So again, we're using our elimination equation for the zero order process. K times T is the drug released, and that's equal to 200 milligrams, as I just described before. Now, I know that T is equal to 200 milligrams over K. So I'm taking this guy here as the denominator. I know K, and therefore the time to release 80% of the drug is 24 hours. This is very nice. Finally, is your time to practice. The first one, 12.3, is asking you to determine the units of the initial concentration. And here you will notice that when C is plotted against time, you have a line, and therefore it must be a zero order process. What are the units of the C0? Okay. In 12.4, you maybe it's the same concentration versus time data we have here. I'm not sure. It doesn't matter anyway. You need to calculate the value of the initial concentration, not the units. In 12.17, you have to choose all the correct statements, and it has to do with your understanding of what is the meaning or the physical significance of the zero order rate constant. So this is very important here. And finally, 12.19 is giving you, is telling you that the metabolism of a drug follows a zero order process, a zero order kinetics process. The rate constant is given to you. If the initial amount here, that would be A0, is 120 milligrams, how much drug is metabolized after 8 hours? So this is, you need to calculate the drug metabolized. So you can do that by calculating the product, of course. All right? Enjoy it. And at this point, I would like to thank you for your attention. Until next time.